Let's begin by exploring what field theory really means. In physics, field theory is a framework that helps us understand how properties, like magnetization or density, vary across space and time. Unlike traditional approaches that focus on the average behavior of an entire system, field theory zooms in on local variations, capturing the richness of how things change from one region to another. This perspective is crucial for studying complex systems, especially when local fluctuations matter. By shifting our focus from individual particles to continuous fields, we gain powerful tools to describe and predict physical phenomena in a wide range of systems. Central to field theory is the concept of the order parameter field. Think of the order parameter as a quantity that tells us about the state of a system at each point in space. For example, in a magnet, it could represent the local magnetization. By considering the order parameter as a field, we allow it to vary from place to place, capturing the system's spatial complexity. This approach stands in contrast to methods that use a single average value, which can miss important details about local behavior. The order parameter field is our window into the microscopic world, revealing patterns and transitions that would otherwise remain hidden. Traditional Landau theory typically uses a single average value to describe the entire system. While this works for some cases, it falls short when spatial variations are significant. Field theory, on the other hand, is designed to handle these variations. By treating the order parameter as a field that can change from point to point, we capture a much richer picture of the system's behavior. This is especially important in systems where local fluctuations drive important phenomena, such as phase transitions or pattern formation. Field theory thus extends the reach of classical approaches, offering deeper insights into complex systems. A key step in constructing field theory is coarse graining. This process bridges the gap between microscopic particles and macroscopic fields. Imagine dividing the system into many small regions, or cells. Each cell is large enough to contain many particles, but small enough to capture local variations. Within each cell, we average the properties of all the particles to define the order parameter at that location. This averaging smooths out microscopic details, allowing us to treat the system as a continuous field. Coarse graining is what makes field theory practical for studying large, complex systems. Let's look closer at how we divide the system. The idea is to split the entire space into many cells or blocks. Each cell should be much larger than the distance between individual particles, ensuring that it contains enough particles for meaningful averaging. At the same time, the cells must be small enough to reflect changes that happen on a macroscopic scale. This careful balance allows us to capture both the collective behavior of particles and the spatial variations that matter for the system's overall properties. Choosing the right scale for each cell is crucial. The cells must be large compared to the distance between particles or the range of their interactions. This ensures that the order parameter represents an average over many particles, smoothing out random fluctuations. However, the cells can't be too large, or we'd lose important information about how the system changes from place to place. The art of coarse graining lies in finding the sweet spot, where we capture essential variations without getting lost in microscopic noise. Within each cell, we calculate the average value of the property we care about. This is our order parameter at position X, for instance. If we're studying magnetism, we'd average the magnetic moments of all particles in the cell. This average becomes the value of the field at that point. By repeating this process for every cell, we build up a continuous field that describes the system's behavior across space. This method transforms a complex, particle-based system into a smooth, manageable field. After coarse graining, the order parameter field can be treated as a continuous classical variable. This means we no longer track individual particles, but instead focus on how the field changes smoothly across space. This shift greatly simplifies our analysis, making it possible to use powerful mathematical tools from calculus and differential equations. The continuous field captures the essence of the system's behavior, allowing us to study phenomena like waves, patterns, and transitions in a unified way. Now let's introduce the partition function, a central concept in statistical physics. In field theory, the partition function sums over all possible configurations of the field, weighted by their energy. It's written as an integral over all field paths, with the Hamiltonian determining the energy of each configuration. The partition function encodes all the thermodynamic information about the system, such as its average energy, fluctuations, and response to external fields. By calculating the partition function, we can predict how the system behaves under different conditions. Hamiltonian plays a crucial role in field theory. It's a functional that assigns an energy to every possible configuration of the field. In our context, the Hamiltonian depends on the order parameter field and possibly on external influences, like a field Hx. The lower the energy, the more likely that configuration is to occur. The Hamiltonian thus shapes the landscape of possible states, guiding the system toward its most probable behaviors. Understanding the Hamiltonian is key to unlocking the predictions of field theory. The partition function, the symbol D, represents the integration measure. This tells us to sum over all possible field configurations, not just a few. It's a way of accounting for every way the field could vary across space. This comprehensive approach ensures that our predictions include all possible fluctuations and arrangements, making the theory robust and reliable. The integration measure is a subtle but essential part of the mathematical machinery behind field theory. Sometimes the system is influenced by an external field, denoted as Hx. This could represent a magnetic field, an applied force, or any other external influence that varies across space. The presence of Hx modifies the energy landscape, favoring certain configurations of the order parameter field. By including Hx in our theory, we can study how the system responds to external stimuli, revealing new behaviors and transitions that wouldn't occur otherwise. Temperature, represented by T in the partition function, controls the importance of energy differences between configurations. At high temperatures, the system explores a wide range of configurations, while at low temperatures, it settles into the lowest energy states. Temperature thus acts as a tuning knob, determining how much the system fluctuates and how sharply it responds to changes. This interplay between energy and temperature is at the heart of statistical physics and field theory. For practical calculations, physicists often use a phenomenological approach known as 5-4 theory. In this framework, the Hamiltonian includes terms that depend on the order parameter and its spatial variations. The 5-4 term captures the essential physics of many systems near phase transitions, where fluctuations become important. This approach provides a manageable way to calculate properties like correlation lengths and critical exponents, making it a cornerstone of modern field theory. While 5-4 theory is powerful for describing long wavelength, macroscopic behavior, it has its limits. Specifically, it doesn't capture the energy associated with short wavelength, microscopic details. These finer features require more detailed models or additional terms in the Hamiltonian. Recognizing the strengths and limitations of 5-4 theory helps us choose the right tools for different problems, ensuring that our models are both accurate and efficient.